I located this document in my mess. Decided it covered things pretty well. And I picked out a few. Let's see, where's my copy? Here. Okay. So the questions are all in the same style that I'll give you on the exam. Let's see. So actually I picked out quite a few of them. I think some of them are basically just memory work. Some of them are really short reasoning. So for instance, this first one. Scroll up since I got so many of them to do on the same page. Oh, there we go. We get two of them in anyway. So which of the following groupings are the three terms closely related? So you really have to look at each one and see if they're related at all. Kinetic energy and energy of motion, yeah, those two are related, but cohesive forces, not so much. I think disruptive forces would be more closely associated with kinetic energy. So potential energy doesn't work with that one. Kinetic, electrostatic, potential, electrostatic, cohesive. I think this one probably is the best one, D. Probably should have. Yeah, trying to check myself. So my reasoning was sound according to the key. The phrase is particles close together and held in fixed positions. Close together, fixed positions, and completely fill the container. Apply respectively to. Okay, so you've got two different things going on here. This is one type, this is one phase, and this is a different phase. So the particles together in fixed positions have to be solids. Right? So you can go down and say, all right, well, that's only one. Because the rest of them are not fixed positions, only the solids. So we're done. Test taking technique. Let's see, 3. I swear by the next semester I'm going to have a scrolling mouse. No matter what it costs. So how many times larger in size is the atmospheric pressure unit than the millimeter mercury pressure unit? You just need to say, all right, what is that? What is the conversion factor for atmospheres? Right? So if this one is represented by that one, then each unit of this is 1/760th of that one. See, here's a good rule of thumb. If the unit relationships, if this is the smaller one, then the unit itself is the big. If this is the bigger one, then the unit itself is the smaller one. It helps it put things in perspective. Oh, so that's C would be the answer for that. Okay. 4, yeah, let's look at 4. Indicate what the missing words are in the following statement of Charles' law. Okay, remember Charles' law. What two factors are related in Charles' law? Well, let's start with what 4 factors are required to describe a gas completely in its physical state? Pressure, volume, temperature, and moles. Those 4, that's all you need. So Charles relates these 2. Then you have to say, all right, well, in this case, yeah, you do need volume over temperature equals a constant. That's Charles' law. So if this is the case, whenever you have a quotient, 2 variables in a quotient relationship equal to a constant, they're always directly proportional. Because if this one goes up, that one's got to go up or it's not constant anymore. Okay. So direct proportional, okay, it's one of these right here. Temperature has to be in Kelvin. Right. Right. If it's not in Kelvin, then it won't work. You remember why? Say we were using Celsius instead of Kelvin. What's the problem with that? Eventually, Celsius goes negative. You can't have negatives in these calculations. It just blows everything up.
Kelvin only goes to 0.
Right. Kelvin starts at 0, so it's always positive. Okay. That's 4. Let me see. I might do every one for the first few. 5, 6, and 7. Okay, we do 5. The correct form of the equation for the ideal gas law. So you remember well, actually, it's there. You remember the ideal gas law? Like that. PV equals NR. Oh, no, that's not it. PV equals nRT. Here we go. It's A. Sometimes these questions are tricky. And let's say, all right, which is the ideal gas law? And it'll solve for one of them. It'll say like this. And try to throw you off. But no, that one is given in legitimate form, or the most commonly presented form of the ideal gas law. Actually, if you're putting the law together in terms of Boyle's law, Charles' law, Avogadro's law, they're all something equal to a constant. So if we wrote this one equal to a constant, the constant would be R, right? And then it would be PV over NT. And that would be consistent with our other laws. Only that R is special. Because if you know that, if you have the right units, if the units here match that, then you don't need a before and after situation. You say, what is my current state? And you can solve for it because R is fixed. If you use the right units. Okay. Yeah, 6 and 7. What's the volume in liters occupied by 2.12 moles of nitrogen gas at 0.75 atmosphere pressure and a temperature of 55 degrees? So we ask ourselves, is this a before and after or a state? I don't see any afters. They're all befores. You only have those moles, those atmospheres, that temperature, and it asks you for the volume. So if we know this one, this one, this one, we can find that one if we use the ideal gas equation. So we're going to be solving for volume, right? Come in. Are you there?
Yeah.
Grab one of these also. Okay, so what we need to do is say, all right, do we have the right units? Well, R is, and that's liter atmospheres per mole. Okay. So we need moles is good. Atmospheres is good. Temperature is not good. Right. So let's see, that's 8 to 328 K. I think. Yeah. So we just plug in those numbers. That one, moles is 2.12 here. And then I'm going to go off screen if I do that. Put it down here. Temperature is 328 here, and then divide by pressure, which is 0.745 atmospheres. So we have to match all the units, and the constant tells you what the units have to be. All right, then we do a little number crunching. That's the thinking part. The rest is just learning how to operate your calculator. 0.08206. 328. Okay, I get it. Let's see, how many significant figures? 3. 76.5. And we're looking for volume, liters. Close enough. That's the best answer. There must have been some rounding. 2.12, no, 8, 12, 3. Wait a minute. No, they're right. I rounded wrong. That's it. Yeah, 76.6 liters. And all you have to do, the really hard part is deciding what to do with the information. I mean, how do you solve that equation? Is it, for most gases, when you do these types of calculations, it's either before and after or state function. All right. Let's move on. We're going to do 7. Yep, let's skip 7. Partial pressure of helium in a gaseous mixture of helium and nitrogen trifluoride is the partial pressure. This sounds to me like a definition. The partial pressure of helium in a mixture is the pressure that helium would exert in the absence of the nitrogen trifluoride. Yeah. I'll go with A. Let's see if B, C, or D has anything to offer. Percentage of the total pressure of the mixture. Percentage of the total pressure. Actually, it's not, it's percentage, it's mole fraction of the total pressure. Equal to the total pressure divided by helium's, no, sorry. Equal to the total pressure divided by the number of helium atoms. Nope. I think our best answer is A. It's the pressure of helium. It's like they're independent actors. The partial pressure is whatever the pressure would be, helium by itself. According to Dalton's law of partial pressures, the total pressures just add up all the individuals. They act independently. So that one should be A. Yeah, the key agrees with me anyway. Okay. Let's move to number 9. There we go. Scribbles off of there. Which of the following is not a factor in determining the magnitude of the vapor pressure of a liquid? So what are we talking about with the vapor pressure? If you have a container with a plug in it, and you have liquid down here, then it's going to evaporate. Right? It's going to evaporate, make a gas, and it's going to exert a pressure. And at some point, the evaporation and the condensation are equal in rates. So it establishes, at a given temperature, a fixed temperature, the pressure in that headspace. And it depends on the nature of the gas, of the liquid, as to what that pressure is. Some make higher pressures than others. Like diethyl ether, you make a huge vapor pressure. Water, not so much. But what factors are involved? Which is not a factor in determining the magnitude of the vapor pressure. The temperature of the liquid, not. You increase the temperature, that pressure is going up. So that's a factor. The strength of the attractive forces between molecules, that's a factor. Remember I said water has one type of pressure and diethyl ether. Okay, let's use the example that we covered in class. Same molecular formula, different structure. Let's see. Ethanol, the drinking kind. And then the same formula, dimethyl ether. Right? This one has a much, much higher vapor pressure because of its structure. And its structure allows it to have less interaction with its neighbors. Whereas this one has the opportunity for hydrogen bonding. We talk about hydrogen bonding? I think so. So the hydrogen bonding makes the attraction to its neighbors much stronger. So its vapor pressure is going to be lower than this one. Okay, so that is a factor also, the strength of the attractive forces. The size of the container for the liquid, no, doesn't have anything to do with it. As long as you've got liquid down here, then the vapor pressure is going to stabilize at the same value. It's an intensive property. The only thing that could mess it up is if you don't have enough liquid. And then it all evaporates before the equilibrium is established. That could mess you up. The type of forces between molecules within the liquid, yes. That's sort of another way of saying B. B and D are joined at the hip. Okay, let's see, that was 9. So the one that doesn't fit, is that what it was looking for? Which is the phone? Yeah, the size of the container doesn't fit. How about 10? I have to scroll that one. Okay. A liquid is placed in a closed container. Equilibrium is reached when? Well, we already talked about that. Equilibrium is reached when the rate of evaporation and the rate of condensation are equal. Those two rates. Let's see, when the rate, here we go. The rate of condensation equals the rate of evaporation. That's what equilibrium, that's the definition for this type of equilibrium. Actually, there are lots of types of equilibrium, and they usually revolve around balanced rates. Chemical equilibrium is the same way. When you have a reaction going from reactants to products, they can go backwards too. But as long as the rates are balanced, then you're at equilibrium. So it's always a rate question. Liquids will boil at lower temperatures at higher elevations because. Okay. Yeah, be sure and grab a lamp. Liquids will boil at lower temperatures at higher elevations because the intermolecular attractions are weaker. No, they don't change. Will boil at lower temperatures, higher elevations. Atmospheric pressure increases. No, at higher elevations, it decreases. It is harder to transfer heat to the liquid. No problem there. The vapor pressure at which boiling occurs is lower. That's it. Actually, this is another way of saying this is that the atmospheric pressure is lower. So if you think about it, when the liquid is trying to evaporate, it's got an opposing pressure. So as the molecules leave the surface, they've got to fight that pressure on the surface. Let's see, whose law was it? Henry's law. You increase the amount of gas dissolved in the liquid if you increase its pressure. It's driving more gas molecules into the solution. Or you can look at that also in terms of the vapor of that liquid. If you increase the pressure, it's going to drive more. It's going to be more difficult for it to oppose that pressure. So you increase the temperature, and it increases the kinetic energy of the molecules at the surface. And now more of them can move into the vapor phase. So it all has to do with that external pressure. If you go to Denver and try to boil an egg, it'll take you longer than 3 minutes to get a soft boiled egg. Because the air pressure's lower, so the water boils at a lower temperature. And the egg cooks depending on temperature. I wouldn't want to boil an egg on top of Mount Everest or anywhere near it, like base camp. It'd take forever. So they probably have MREs with.
I was thinking, you can stay up there long enough to start cooking.
Yeah, well, you probably have to breathe oxygen while you're waiting for your egg to boil. Okay, that was 11. Yeah, 12. Which of the following statements about intermolecular forces is incorrect? So this drives home the point that attention to detail may save your bacon, right? If you're a speed reader, you're not reading a novel here. You're reading a test question. So look at every word and how they fit together. Which one is incorrect? Okay. They must be overcome. These intermolecular forces must be overcome in order for molecules to escape from the liquid state into the vapor. That's true. And you have to overcome those forces in order to do that. The lower the forces, the more that you can move into the vapor phase and the higher the pressure. They're much weaker than intramolecular forces. That's true too. Like intermolecular, the forces between molecules has to be less than the forces within the molecule, holding it together. If it wasn't, then those intermolecular forces would just rip the molecule apart. So A and B are true. They are electrostatic in origin, these intermolecular forces. That's true. Yeah, it's for instance, the hydrogen bonding, like where you have something like that, this is on the end of the molecule. What you have is an uneven distribution of electron density here. So you have electrostatic difference, slightly negative here, slightly positive there, and that sets up for attractions. Okay, so the last one is our best candidate. They occur within molecules rather than between. No, it's the other way around. Intermolecular forces occur between molecules. They still say intramural, intramural games, sports games. They used to when I was a kid. Intramural games were within the school. Like you'd have A team playing B team or something like that. But intramural games were between schools. Okay. All right, so the best answer is D. 13? Yeah, let's look at 13. Which of the following liquids would London forces be the predominant intermolecular force? Remember what London, actually the full name is London Dispersion. London Dispersion forces. By the way, first of all, how are they ranked in strength? The strongest forces are intramolecular. They can be covalent bonds, they can be ionic bonds. Actually, when we're talking about molecules, we don't talk about ionic bonds because they don't form molecules, they form crystal lattice. So we'll set that aside for now. The intramoleculars are the strongest. And then you go down to dipole. The dipole-dipole interaction. We did cover this, didn't we? Okay. Dipole-dipoles. And then actually the strongest of the dipole-dipoles are the hydrogen bonds. So they're kind of together. And then below that, the weakest are the London forces. Okay. So when with the London forces would we even consider them? When these guys, of course, those intramolecular forces don't count because these are intermolecular forces. And the question is in which of the following liquids would London forces be predominant as intermolecular forces? So we just don't consider those. So it's between dipole and London. Dipole forces are between permanent charges. They're not full charges, not like sodium plus ion. They're more like slight charges, where I use that delta symbol. Just slight differences, but they're permanent. London dispersion forces are intermittent. They come and go in a nanosecond. They're here and gone. So they're a lot weaker than these. So when would these be, well, let me ask you this question. Do the London forces appear and disappear? Well, I just said they occur in a nanosecond, but what I mean is, I'll just tell you. I will regurgitate the lecture. London forces are always there. Dipole, not so much. It depends on the structure of the molecule. But London forces, no matter what the molecule is, they're always there. So when would they be dominant? Well, these guys aren't there. Right? When you don't have dipole interactions, that's all you got left. Okay, so then you look at your molecules and say, all right, which one of these would not have dipole? That's where the London would dominate. So we look at the structure of the molecules. That's not supposed to be there. It's just supposed to be a dinitrogen molecule. So you want to look at the structure of the molecule and whether or not you see a dipole possible. Right? So if you have HCN, you have different atoms there that could cause even a slight dipole. Right? They have differential attraction to electrons. That's the key. When they're bonded together, one of them, they don't share equally, right? So how about this one? Right. That one definitely not polar because these guys are equal. I mean, they pull on electrons the same. So this one would have no dipole interaction whatsoever. That's your best answer. If you look at the others, you've got a sulfur versus hydrogen, right? That's hydrogen bonding right there, or pretty close to it. And IF, iodine and fluorine together, they may be halogens, but one of them is a stronger. In fact, fluorine is the strongest attractor of electrons in a bond with any other element. Did we talk about electronegativity? Okay, it's the most electronegative on the periodic table. And then below it, iodine is less electronegative. So you would have a dipole developed here, there, and there, but none there. So the short version is the one that has no dipole is the one where London force is predominant. Okay. All right. Oh, I know why that's it. That A is abbreviation. That's for answer. The answer to that one. So I must have gone through and marked the answers and forgot to remove that indicator at some point. Okay. Let's see. My goodness, 14. Which of the following descriptions apply to matter in a solid state? I probably shouldn't have this one here because we've already talked about it. Definite shape, right? Definite shape and definite volume for sure. But do solids have high density? Well, yeah, they do. So this is a good candidate right here. Cohesive forces dominate over disruptive forces. Yeah, that's true also. Kinetic energy dominates over potential. No. If that were the case, then you'd have a gas. More than one correct response. Okay, there you go. A and B are both good answers. All right, let's see. Yep, keep going. Which of the following samples of gas would have a new volume of 3 liters if the pressure is decreased from 3 to 1 atmosphere at constant temperature? So we're going from volume and pressure. That's Boyle's law. Right? So which of the following samples of gas would have a new volume of 3 liters? So a new volume is here, 3 liters. And it's going from 3 atmospheres to 1 atmosphere. So here's 1 atmosphere, and here's 3 atmospheres. And there's our unknown. Okay? Yeah, okay. So if we solve for this one, volume is 1, right? 1 liter. Right? Take 3 into this one, you have 1. So we're looking for the one that starts with 1 liter. Oh, there it is right there. Okay. That's a roundabout way of asking you to do that calculation.
So why are there like heat, like why are there a helium beside of us? If we,
To throw you off. Because they're
I was
all,
like, what?
yeah, you treat them like, for Boyle's law, doesn't matter what the gas is. Right? That's the whole point behind gas laws. It doesn't matter what the gas is, as long as the conditions are simulate ideal behavior. And by the way, what conditions simulate ideal behavior in any gas? High temperature, low pressure. Okay. And by inference, low moles. I don't know if I mentioned that one. High temperature, low pressure, low moles. And under those circumstances, your gas is going to behave ideally. Now, what do we mean by high temperature? Room temperature. 20 plus 273 is 293 K. That's high relative to absolute zero. Low pressure. Low pressure is 1 atmosphere relative to what? 50 atmospheres, 100 atmospheres. When you get up to those pressures, the gases stop behaving ideally. And then you need the correction factors. I don't know if I didn't show you those. Okay, don't worry about that. Okay, 16, yes. Which of the following is a correct equation for the combined gas law? Okay, now here they are, they're rearranging things to try to confuse you. Right? So start with the combined gas law that's in your head. P1 V1 over N1 T1, right? Equals P2 V2 over N2 T2. That's the combined gas law. Then, I guess you'd have to solve it for each one just to see which one works. If you hold the P on one side, then the V2 comes over here. No, that doesn't work. If you hold the V2 constant and you put the N2 and T2 over here, that doesn't work. If you hold the T2 constant on one side, it has to go over here. That means P1, V1 goes over here. None of them are correct. Yeah, that's right. None of them are correct. Oh, there it is. That was tricky. Not only did they rearrange the equations, none of them are right. 17.
I hate none are correct or all are correct.
I know.
I hate it with everything in me.
It always leaves you guessing,
Mhm.
second guessing yourself. Yeah. When the vapor pressure of a liquid equals atmospheric pressure, okay, the temperature of the liquid equals what? Well, it doesn't say what the liquid is, so we can't put a value to it because we don't know what the liquid is. What are we talking about here? When the vapor pressure equals the atmospheric pressure, we're talking about the boiling point. Right? That's when the liquid boils. So can't be this one because there's a value and we don't know what the liquid The boiling point of the liquid, there it is right there. Now, why would it not be the normal boiling point of the liquid?
Because we don't know what liquid it is.
We don't know. It didn't tell us that these are standard conditions. Normal means standard conditions, which is 1 atmosphere. If it said when the vapor pressure of the liquid equals 1 atmosphere pressure, the temperature of the liquid equals the normal boiling point of the liquid. That would have been tricky too. Okay, let's see, 18. Yep. My goodness. The intermolecular forces differ from intramolecular forces in that what? They occur only in liquids. I don't think so. They are much larger, much stronger. No, it's the other way around. The intermolecular forces are weaker than the intramolecular forces. They occur only when hydrogen atoms, no, that's not. Oh, there's your favorite answer again. There's no correct response.
I hate it.
I hate when there's more than one correct and then no correct, because then I'm like, oh gosh.
Oh,
I
no.
know.
This one seems correct, but none of the other ones do.
It makes you doubt your sanity, right?
Oh, yeah.
I don't think we have sanity anymore at this point. Probably.
No.
No, you can't afford it. 19. Yep, 19. In which of the following pairs of molecules will the first listed member of the pair have a higher boiling point than the second listed member? Okay, in order to answer this one, you have to assess their relative intermolecular forces, right? You got one over here and one in here in separate containers, and they're only interacting with their neighbors. They're identical twins. Then you say something about their boiling points. Okay, the first one has to be a higher boiling point than the second one. See, listed member of the pair, higher boiling point than the second one. Okay. As a general rule, well, the process of elimination. Let's see. We got our favorite answers again. O2 and NO. Let's go backwards. O2 and NO. What do you have here? Well, here, the only forces that act here are London dispersion, because you've got an oxygen bound to an oxygen, right? So you've got no polar nature to it. This one has a polar nature. Let me see, I think it's a double bond. But this one would be higher than the first one, so that one can't be it. How about this one? Fluorine and chlorine. Well, we have, they're nonpolar, right? So London dispersion acts, but one of them might have a higher London dispersion force acting than the other. And the key to this one is, how big is the atom? How big is the molecule? Chlorine is bigger than fluorine, right? Just look on periodic table. It's below. So it's a bigger atom, which means it's a bigger molecule. And the way London dispersion forces work, I don't think I went over this in class. The way they work is they're higher, the magnitude is greater if you have a larger volume. So what that means is you have more opportunity for the electrons to redistribute in a larger volume than you do in a smaller volume. Okay. So when that happens, the London dispersion forces for this one would be greater than that. So that one's not it. So the question is, does this answer the question? If that one doesn't answer the question, then we're down here. So let's look at HF and HBr. Okay, these two halogens are bound to the same atom in different molecules. Right? So what we have to do is say, what's the difference between this electronegativity and that one, and this one and that one? So we look at the chart and say, okay, that's more electronegative than this one. So the distribution is going to be greater here and lesser here. This is more polar. So the boiling point for this one should be higher. The intermolecular forces should be stronger. That one answers the question. Does that make sense? Okay. No? Well, at least it's not this one. It all has to do with electronegativity and the resultant polar nature of the molecule.
No, I was wrong. Number 20 is my most hated question.
Yeah.
Oh, yeah.
Oh,
These guys are, they can get real messy. And they take a lot of time because you have to look at every answer to see if it's true or false. Sublimation and deposition are opposite changes of state. Sublimation is solid to gas. Deposition is gas to solid. Okay, that one's true. That one's true. A pressure of 1 atmosphere is greater in magnitude than pressure of 720 torr. Yeah, 1 atmosphere is 760 torr. Okay.
Threw me off. There's 700 in there.
Mm-hmm. 1 atmosphere is greater than 720 torr. You have to understand that torr is the same as millimeters of mercury. The boiling point of a liquid can be increased by heating the liquid to a higher temperature. No, you don't change the boiling point. Pressure will do it, but not temperature. So 1 and 2, 2 of the 3 are true. B is the answer for this one. Okay. I think I've already made out the exam. And these kind of questions, I'll give you a hint. These kind of questions occur only in the bonus section. Okay, so you can do them or not do them.
True and false.
I'm sorry?
True and false questions.
The ones that have the multiple answers and you have to figure out how many of them are true? Yeah. I'm pretty sure that's true. In fact, I know it is. Because I don't like these either. But I said, okay, if I'm going to make bonus questions, they need to be a little more difficult to make it worth a while. So I put these type in the bonus section. They're not all this type, but some of them are. Okay, let's see. We already did that one, didn't we? Yeah, we did. 21. Otherwise, I wouldn't be even going over them. But if this type is going to be in the test, we should get some experience. Associated with Charles' law is the concept that if the temperature of a gas increases, the volume of the gas also increases. Oh yeah, that's true. That is the statement of Charles' law. Volume and temperature are directly related, proportional. Liquids show little change in volume with changes in temperature. The key here is little. Volume does change with temperature, but not very much. Now, gases a lot and change. Gases change a lot with their changes in temperature. I mean, based on this law. So this one is true. There's just a little bit of a change. Dipole-dipole interactions are examples of intramolecular forces. And hydrogen bonds are intermolecular. No, they're both intermolecular. So 3 is false. It's just, there's the key word right there. It's not, this one doesn't belong in that sentence. So 1 and 2 are true. Let's see, 22, yeah, 22. We're on a roll, might as well do another one. Okay. Both dipole-dipole interactions and hydrogen bonds are stronger than most single covalent bonds. That's false. These are intramolecular forces. These covalent bonds, they have to be stronger than these guys, the intermolecular forces. So 1's false, 2, the value of ideal gas constant is the same for all gases under ordinary conditions of pressure, volume, and temperature. Ideal gas constant. Yes. That's why we call it a constant. Both condensation and freezing are endothermic changes of state. Condensation, when you go from a gas to a liquid, you're giving off heat. So only one of these is true. Right, this one right here. Only one is true. Let's see. Oh, good, we get to skip that one. 23, 24, 25. Well, 25 is another true false. I just went too far. Here we go. Water's boiling point is much lower than expected based on comparison with other substances because of hydrogen bonding. That's true. You wouldn't expect water to be have such a high boiling point, except for that characteristic right there. The hydrogen bonding does it. In the gaseous state, disruptive forces and cohesive forces are about the same magnitude. No, that's liquids. Those two forces, the ones that hold them together versus the ones that pull them apart, they're about equal for liquids. The disruptive forces are much lower for solids, and the disruptive forces are much, much higher for gases. So this one is false. As liquid surface area increases, the rate of evaporation of the liquid increases because molecules encounter less external pressure. No. The external pressure is an intensive factor. It's the same no matter what the surface area is. So that's not the reason. So we only got one true one in there, right?
Yeah.
Yeah, this one right here. Why does the rate of evaporation increase as the surface area increases? Because you got more molecules leaving the surface, right? They're experiencing the same pressure, but if you got more surface area, then they're going to, say you take the same volume of liquid, you put it in two different containers. One is like this narrow tube. It's only got this much surface area to evaporate. And then you take that same volume and you put it in a pan. Which one's going to be gone first? Right. It's got more surface area. There's just more opportunity for molecules to escape the surface. Right? It has nothing to do with the external pressure. External pressure is the same on both of them. Okay. 26? Okay. We're back to normal questions. So I have to do that. For each of the physical state characterizations, select from the response list the physical state or states to which characterizations apply. Oh, so we're going to match this right here, indefinite shape, with one of these. Indefinite shape. Well, that's liquids and gases, right?
Mm-hmm.
Yeah, liquids and gases. So gases and liquids, here we go. That's it right there, D. This one is definite volume. So which has definite volume? Liquids and solids. Liquids and solids, here we go, C. 28, yeah. 28 also. For, potential energy dominates over kinetic energy. There's only one that satisfies that. The potential energy of a solid dominates over the kinetic energy. That's what holds it together. So the solid state is the only one that answers that. For the liquid state, they're about equal. The potential cohesive forces versus the disruptive forces. That's what we're talking about. Let's see. Are we doing 29 also? Flip the page. Yep. Particles are relatively close together. Let's say solids definitely. Liquids too. The only difference between a solid and a liquid, well, not the only, but one of the major ones is the solid, the molecules, the particles are locked in place. That's why they can hold their shape. But liquids, they're still close together, but there's enough kinetic energy so they can slide past one another, overcome those attractive forces. So both of them, both liquids and solids satisfy. Particles are relatively close together. 30. Yep. Yeah, because 31's on the list too. Consider the expression of gas laws. Select the correct name for this one. P1 V1 equals P2 V2. Pressure volume, Boyle's law, right?
That's one I like.
How about this one? Volume over temperature, volume over temperature.
The B.
This one? No, that's not combined. I don't see any moles or pressure in there.
C.
Yes, Charles law. Volume temperature. Let's see. Or we could say it this way. Let's see, 32. V1 T2, V2 T1. Just rearrange Charles' laws all.
Trying to confuse us.
Mm-hmm. Yeah, that's my job. No, my job is to help you understand this stuff. Whoever made up these questions is bent on confusing the students. Let's see, about 34. Yeah, they're all down there. Consider the change of state. Select the name of the change of state for when energy is absorbed. Got all of them? Yeah, they're all there. So under what change of state do we have energy absorption? You've got to go from either a solid to a liquid or a liquid to a gas or a solid to a gas to absorb energy. You got to add energy to make it go, to make the molecules more excited and spread out to make a liquid, to make a gas. So sublimation, yep, you got to add energy to that one. Condensation, no, that's exothermic. This is endothermic, that's what they're saying. Endothermic deposition, that's exothermic. You're going from a gas to a solid, freezing. You're going from a liquid to a solid. There's only one, sublimation. Right? Think dry ice. When you go from solid carbon dioxide to gaseous carbon dioxide. The reason we use it is because it absorbs energy when it changes state. Right? It keeps things cold, but it doesn't get them wet. Right? It's not like water melting. Okay. And I think the other reason just occurred to me, why dry ice does not get your samples wet in transit. Because as it turns from a solid to a gas, it drives out all the atmosphere. It displaces atmosphere with that CO2. No moisture, no condensation. Let's see, 36, here we go. Characterize the effect that changes will have on the vapor pressure and the boiling point of a liquid by decreasing the temperature of the liquid by 20 degrees at constant pressure. So we're looking at the effect of this temperature change. A negative 20 degree temperature change. Decrease the temperature by 20 degrees and the pressure is constant. Okay, I have to write things on the board. Get them out of those word problems because word problems are meant to confuse. The effect that this change has on the vapor pressure and the boiling point. we're looking at that effect on vapor pressure and the boiling point. Oops. Okay. What effect does it have on the vapor pressure? As you decrease the energy of the liquid, then you're not expelling as much gas from the surface because it doesn't have enough energy. So you should decrease the vapor pressure. So let's see which one's, it's either A or B, right? Because it does change. Okay, so A or B is possible. Now what happens to the boiling point? Boiling point doesn't change, right? The only thing that affects the boiling point is the external pressure. So it's gonna boil. It won't be at minus 20, whatever minus 20 was. So it does not change. There you go, decrease. So the answer to this one is B. Okay. $36. Let's go to 38. Oops. There we go. The following intermolecular force descriptions. For each of these, select the correct name from the response list. Permanent electrostatic interaction between polar molecules in which no hydrogen is present. So when you're thinking permanent electrostatic difference, that has to be a dipole. It's not, it's a polar molecule, so it's not an ion. Can't be an ion based on this description. It has to be a molecule. So a polar molecule has to have a difference between the electronegativity of the atoms, and that's a permanent established charge difference. It's less than a total charge, like +1, +2, -1, -2, but it's still an electrostatic difference. So that's dipole-dipole interaction. Right, it said hydrogen's not involved, so it can't be hydrogen bond. Okay. I'm gonna have to scroll this one. We're gonna have 40. A solution may contain what? Only one solvent, but many solutes. We found our answer. If we look at the rest of them, many solvents, nope. Only one solvent, one solute. Nope. You can have bunches of solutes in it. Many solvents, many, no. We found our answer. You've always had one solvent, and then you can have a whole bunch of solutes in it. Okay, that was 40. 41. Which of the following statements concerning a saturated solution is incorrect? So what do we have with a saturated solution? In other words, the solute is maximum amount possible in the solvent. That's what saturation means. So under what circumstances are we talking about? Undissolved solute must be present. Undissolved solute must be present. Well, yeah, that's the only way you can establish that it's saturated. If there's some solute that will not go into solution, that's one way to establish it. Undissolved solute may or may not be present. Well, that's also true. Actually, this is true. B is truer than A. Why? Because I can make a saturated solution with a solid in it and then filter the solid out, and it's still saturated. Okay, so I think B is probably a better answer. Undissolved solute, if present, is continually dissolving. Well, that's not a completed statement. Undissolved solute, if present, is in equilibrium with the dissolved solute. That's the best answer right there, I think.
I said, oh gosh.
Let me see.
So you're telling me A, B, and D are right?
But
Well-
then it's dry.
But these the best.
Undissolved solute, if present, is in equilibrium with dissolved solute. Yeah, that's a bad question, isn't it? Because the key says A is the best answer. Undissolved solute must be present. I don't think so. I think D is a better answer. Undissolved solute, if present, is in equilibrium with the dissolved solute. Yeah.
So if we have a question like that,
God, I hope we don't have one of those Scott so you're right.
Yeah, 41 could be A or D, actually. Either one is valid, I think. Let's see. 42. 43. There we go. 43 is there. For which of the following types of ionic compounds are most examples insoluble in water? Okay, to do this one, you need that that chart, the solubility chart, and it'll be on the exam, the last page. In fact, let me look.
You gave us copies of it.
Yeah, I'm looking at a copy of the exam to be sure. Yeah, it's there. Doesn't have the rules with it though. So, well, you could look on your chart and say which of the following types are most examples inside. Most examples, doesn't have to be all of them, but most of them. Nitrates. So if you take that chart and look at the nitrates and then just go across and look at all the squares under the cations, then you see they're all soluble, every one of them. Right, so A wouldn't be it. How about sulfates? Most examples are insoluble in water or hydroxides. Chlorides, most examples are soluble. So it'd be a fight between sulfates and hydroxides. So let me look at the chart. See if I can solve it this way. Sulfates. Here we go, sulfate. Most are insoluble in water. Now, most are soluble. There are a few insoluble ones. Hydroxides. Hydroxides is a better answer. Right, it's got more gray squares than the rest of them. Okay, 43, 45. What's the molarity of a solution containing 16.7 grams of ammonia in 1.5 liters of solution? All right, what's the definition of molarity? That's where you start. Moles per unit volume, and the volume has to be in liters. So we're good here. And this is liters of solution. So we're good. It's already given to us. We need to find moles of that. So you know how to do that. Molar mass. Right. Right. Cancel grams, leave moles. Whenever you have moles and grams as a quotient, it's molar mass. Can't be anything else. So let's see. Nitrogen is 14.01, I think. Yeah, 14.01. And 3 hydrogens is 3.03. So we need 17.04. So it's going to be, well, this value is going to be less than 1, but then you divide it by that one. So I guess I better calculate it. 16.7 and 17.04 divided into it. That leaves 0.980 moles. per 1.5 liters, which is, let's see, three significant figures. 0.653. There it is right there. Yep. Okay. All right. Time. 46. Well, let me scroll down because I'm 47 also. And 48's there also. Yep, do all three of them. If 145 milliliters of 2 molar KOH is diluted to 1.15 liters, the resulting solution contains how many moles of KOH? Okay. This is a dilution problem. All right, so you have molarity times volume of the concentrated equals molarity times volume of the dilute. Right. So what's the concentrated molarity? 2 molar. And the concentrated volume, 145 milliliters. And the molarity of the diluted is not given, but the final volume is 1.15 liters. Now, this is going to give us molarity, but it's not going to give us moles yet. Right? You know what? This molarity times volume is the moles. This is the moles. Let's see, concentrated dilute. That's why this works, because the moles before are the same as the moles after. So all we have to do is multiply these two together. Actually, 0.145 liters times 2 is what? 0.290 moles. There it is right there. So it was sort of a dilution problem, but we didn't have to go all the way through the dilution part. You have to recognize that the moles before equals the moles after. That's why dilution works. And the question asked is just how many moles. So that's all we had to do is find out how many moles going into the dilution. A colloidal dispersion differs from a suspension in that colloidal particles. What's colloid? My best explanation for a colloid is it looks like a solution, but it's not. And you have to ask yourself why. Why is it not a solution? Because you can still see the particles. I mean, you may need some help, like use a bright light, the Tyndall effect, shine a bright light through it, and you can see the beam. If you can see the beam, then it's not a solution. It's based upon the size of the particles. Right? You got all this kinetic energy in your solvent. Right? All those solvent molecules are just, they're just flying around. So if the particle is small enough, has small enough mass, then impacts with those particles are sufficient to keep it suspended. So with that information in mind, a colloidal dispersion differs from a suspension in that colloidal particles tend to settle. No, colloids do not settle. They're large enough to scatter light. Well, yes, that's true. They're large enough to be seen with the naked eye. Nope. Large enough to be seen with a microscope. Nope. They're too small for a microscope. So large enough to scatter light. That's the Tyndall effect. me see if the key agrees with me. Yep. Okay, 48. Compared to pure water, a 1 molar sugar water solution will have what? Okay, what are we talking about here? We're talking about colligative properties. Changes in vapor pressure. Let's see, what was the one we did before? Freezing point depression, boiling point elevation. All those are colligative properties, and they don't depend upon the nature of the solute. They may have some dependence on the nature of the solvent, but not the solute. So the number of moles of solute that go into the solution is all that matters. Doesn't matter what the identity is. So with that in mind, compared to pure water, if we have a sugar water solution, what is it going to do to the vapor pressure, the boiling point, and the freezing point? Vapor pressure, boiling point, freezing point. Okay. It lowers the vapor pressure because you've got those sugar molecules at the surface competing with the water molecules to go into vapor phase. They're in the way. The sugar has to be non-volatile. If you take general chemistry, will complicate matters, but for now, sugar is non-volatile, so all it does is interfere with the vaporization of pure water. So the vapor pressure is lower. All right, process of elimination, B's out. Can't be B. How about the next one? This is decreases that one. Boiling point. It should increase the boiling point. Okay, so nope. This one should be C. Let's be sure it matches. Lowers the freezing point. That's true. Okay, we found our answer. Let's see, 48. Yeah, 49. Let's see, what time are we supposed to go in the lab? 11, right? Okay. I don't want to miss our lab time because it's not particularly complicated, but it does take time.
Are we going to go in early to talk about the directions?
I probably need to. What's the freezing point for a solution containing 1 mole of sodium chloride dissolved in 1 kilogram of water? The freezing point. All right, now this one, you need more information than is given in this problem. 1 mole of sodium chloride and 1 kilogram of water. So the freezing point, change in temperature for the freezing point is equal to that, let's see, what was it was a K, wasn't it? K freezing point times molality. Moles per kilogram. So we need to know this value right in here. And I think this value is 1.86 for water. If I forgot to give that information, if this type of problem shows up and you know you need that information, just ask me and I'll tell you what it is. So the change in freezing point, right? Freezing point of water is 0 degrees. So what effect does it have on the freezing point? Well, if this molality is 1 mole per kilogram, but is it? What does this make? It makes 2 moles. So actually 2 moles are going into solution. So this would be 2 molal times 1.86. So it'd be 3.72. But this is freezing point depression. So it's that many degrees below its freezing point. So since freezing point is 0, it'd be minus 3.72. There you go, right there. Okay. Yeah, crenation of red blood cells occur when cells are placed in what type of solution? Crenation is when they kind of shrivel up. So what causes them to do that? They're losing water, correct? So they would have to lose water in a hypertonic solution. Here. I don't know what's the opposite of crenation.
Well, when they swell.
Swelling, that's a good word, yeah. If they swell, it's the other way around. Hypotonic solution. We're going to do that today. Not with red blood cells, though.
Oh.
We're going to use potato cores. I'm going to core out a piece of potato.
That would have been so cool if we could
Yeah.
swell up a red blood cell.
Well, we'd have to use a microscope to see it.
I'm burning out on the microscope.
Yeah.
We had 20 differentials we have to do. Well, we're going to do Tuesday. But we want to talk about being burned out on this microscope. Yeah, that would be.
Which of the following solutions is hypertonic with respect to blood? Sodium chloride, glucose. Okay, you've got two comparisons here. One is sodium chloride, and one is glucose. So the physiological saline solution here, sodium chloride, is 0.9%, approximately. So that would be isotonic. What is it for glucose? Remember the abbreviation that we, D5W, dextrose 5% by weight, is what that means. All EMTs know that. This is 5%. Okay, so we compare which one of these is hypertonic. 0.5%, 0.7, no, it's lower than that. So it can't be that. Can't be this one, has to be that one right there. 7.6% glucose. And glucose is a molecule, right? It's C6H12O6. But sometimes it's cheaper just not to purify it. If you know that you've got 6 carbon sugars in there, you just say dextrose. And it could be mostly glucose, but it could have some others in there. Like fructose is 6 carbons, galactose is 6 carbons, a bunch of others. So sometimes they just say dextrose, saves them the cost of purifying it. And it serves the same purpose. I mean, if you just need a isotonic solution, then 5% dextrose will serve the purpose. Sodium chloride 0.9% in a pinch will do it if you're trying to replace body fluids. But you don't want to keep your patient on that for very long because you're overloading their kidneys with sodium and chlorine. And of course, if they're diabetic, then give them glucose. Well, I guess you have to weigh the possibilities. What's your priority? You know, do you want to deal with diabetes, or you want to save their life from blood loss? I kind of have to make a decision there. Deal with the diabetes later. Okay. Why have I got so many? Which of the following statements about solutions is correct? A solution is a homogeneous mixture. Well, yeah, that's true. Uh-oh. More than one correct response.
Oh.
Okay. Well, this one, we found a true one already. Okay. It's possible to have solutions in which both solvent are solids. Yeah, that's true also. Yeah. Brass is an example. Copper and nickel.
Why do they do this stuff?
Out of meanness. Solutions readily separate into solute solvent if left undisturbed for 24 hours. No. That's suspensions. So more than one correct response, that's true. A and B are actually true answers. 53, a crystal of solid sodium chloride is placed in an aqueous sodium chloride solution. So we got sodium chloride solution here, aqueous, and we're going to drop a chunk of solid sodium chloride in there. Okay. It's observed that most, but not all, the crystal dissolves. So some of it dissolved, but not all of it. This means the original solution was what? Well, if some of it dissolved, that definitely means it wasn't saturated, because there's still room for some more solid to go into solution. So it was unsaturated. We can't say that it was dilute. Unsaturated is the only one that we can say based on that evidence. Let's see, does the key agree with me? Yeah, it was unsaturated. Let's see. Consider the following substances and their polarities. A is polar, B is polar, C is nonpolar, D is nonpolar. It is true that what? A is more soluble. So we got these two polars. So they will be soluble in one another. And C and D will be soluble in one another, but they won't cross. A is not soluble in C or D, or it's less soluble because like dissolves like. Polarity matters. A is more soluble in C than B. No, A is more soluble in B. C is more soluble in D. C, yeah, that's true. C is more soluble in D than it is in A. So let's see, we've got more than one correct possible. D is more soluble in B. D is more soluble in B, no, than it is in C. No, so there's only one answer. B is the answer to that. Let's see. 55, and then we get to skip a few. In which of the following sets of ionic compounds are all members of the set insoluble in water? Okay, now you have to go back to your thing. Let's see. Chlorides. Most chlorides are soluble. Silver chloride is not. Lead chloride, I believe, is not soluble. Right. All members of the set are insoluble. So this is ammonium chloride is soluble. Let me just look it up. Ammonium, where's ammonium? There it is. Yeah, ammonium chloride is soluble. So that one's not it. Most carbonates are insoluble. Copper carbonate. Carbonate is insoluble. Calcium carbonate's insoluble. Actually, all these carbonates. So that's it right there. Oh no, we've got more than one possible. Okay, lead sulfate. Lead sulfate. Where is it? There we go. That's insoluble. Iron 2 sulfate is soluble. All right, okay, so B is the only one that works. All of those members are insoluble. All the carbonates here. Okay, let's skip down to 61. Yeah, they're all there, 61. Which of the following solutions has an osmolarity of 3.0? Osmol of 3.0. Well, what does that mean? Well, an osmolarity, if the molecule does not break up in solution, then the molarity and the osmolarity are the same. If the molecule breaks up into multiple particles, then the osmolarity is the number of particles per molecule times the molarity. So sodium chloride would be twice, calcium chloride would be 3 times. So let's see, if it's 3.0, then let's see, no, glucose would have to be 3.0. 2.0 molar sodium chloride would be 4 osmolau. 1 molar, let's see, that's 4 ions out of that one would be 4. None of them correct. They're all wrong. Right, there's nothing in there. If we had something like calcium chloride at 1 molar, it would be 3 osmolau, because you have 1, 2, 3 ions. Okay? Because the the osmotic pressure of a solution is dependent upon the number of moles of particles that actually go in a solution. And if they break up, you're adding a multiple of particles. Let's see, 62. In which of the following pairings are the terms closely related? All right, hemolysis. Right. That's when it swells too much. Right. Lysis is the word for cut or break apart. So the blood would disintegrate. Hypotonic, ooh, yeah. Hypotonic solution, it would start absorbing water and just blow up. So that's true. Let's see if more than one is correct. Hypertonic, higher osmotic pressure than within the cells. Yeah. Hypertonic is more concentrated solution outside the cell than in. Isotonic solution, no. You get no effect there. So more than one is correct. Oh, we got another true false. Yep. I thought we were done with true false. Okay. Equal volumes of 2 solutions of the same molarity contain the same number of grams of solute. Oh, the key word here is grams. They contain the same moles of solute, but not the same grams. That depends on molar mass. Right? So one is false. Hemolysis and crenation are opposite processes. Okay, I'll go with that. Yeah. The solubility rule, like dissolves like, is not adequate for predicting the solubility of ionic compounds in water. Well, yeah, it is. Water is polar. Ionic compounds are, well, actually, they're ionic. So let me see. Is that one going to be tricky? I would say 1 hemolysis, 2 and 3 would be correct. 63. Yeah, 2 of the 3 statements are true. All right, so they like both 2 and 3 for that answer. Let's see. 65. Let's see. Addition of 40 milliliters of water to 10 milliliters of 8 molar sodium hydroxide would produce a 2 molar sodium hydroxide solution. Okay, so the concentrated is 8 molar, and the volume of that is 10 milliliters. The final volume is addition of 40 milliliters means 50 milliliters final volume. So what's the concentration here? So that's 800 divided by 50. Right? Six. 16. No, 1.6. So that was not true. Henry's law is a pressure solubility relationship for gases. That's true. Boiling points are the basis for the solubility rule. No. So there's really only one. Right? Only one of the statements is true. Yeah. Let's see. How many more of these I gotta go? I don't want to run over. Four. Okay. I think we can make it. Let's see. Didn't we do one like this already? 2 liters of 6 molar solution would contain 12 moles of solute. 2 times 6 is 12. Yeah, that's true. Right? M times V is moles. So one's true. Liquid solutions, volume of the solution is always greater than the sum of the volumes of the solid because of solute-solvent repulsion effects. That's false. It could be greater than, it could be less than. Right. So the first part of that statement is false, so you don't even have to read the rest of it. Osmotic pressure is the amount of pressure needed to prevent the process of osmosis from occurring. Yeah. Right. Remember our example? We had, let's see, we had this container, and then we had this kind of a bulb thing down here with a lip on it, and there's a membrane there. Right? And this one is, say, pure water, and this one is a solution. And the water's moving in. So it rises, right, up to a certain point, and it stops. At that point, this pressure right here, this difference in height, is equal to the pressure that's supplied by that osmotic force. So that's true. And in fact, you can apply external pressure to this and drive it backwards. That's how reverse osmosis works for purifying seawater to make fresh water. 66 and 67. I better scroll down. Okay, for the set of ionic compounds, all these are nitrates: sodium, potassium, ammonium. Choose the correct characterization of their solubilities in water. Actually, they're all soluble. All nitrates are soluble. Right, that's the first rule. And you can look it up in your chart just to verify, but they're all soluble. All 3 salts are soluble. Let's see, 68. For the set of ionic compounds, lithium chloride, silver chloride, magnesium chloride, choose the correct characterization of their solubilities. All right, so this one, how many of those are soluble? I know silver chloride is not soluble. Most chlorides are soluble. So lithium chloride, where is it? No, it's not here. No, it's not. Magnesium chloride. Magnesium chloride soluble. Silver chloride is the only one that's not soluble. So there's only one of the 3 salts. No, wait a minute. 2 of the 3 salts are soluble: lithium chloride and magnesium chloride. That's odd. Lithium's not on the list. Okay, so if that one crops up, just raise your hand and say, it's not on the list, and I'll tell you. Let's see. I think I just got one more we need to deal with. Nope, not that one. The last one. 80. Using the response list below, characterize the osmotic pressure for a 0.8 molar, 0.8% mass volume magnesium chloride. Okay. Oh, okay. So isotonic is 0.9% sodium chloride. So this forms 2 ions. This one forms 3 ions. So if it's 0.8, it's going to be a third again as great as that. So it's going to exceed 0.9 when it does that. That means it's hypertonic. Okay. That's it.